Good morning, class. So today is the lecture number one, and we're just going to give some introductory information for the course for machine design. The first question I have for you is, what do you understand by machine design? What comes to your head? Um, if you think about a machine, it always automatically gives you the idea that something that's in motion, that's moving. It can be something static. Most of the stuff that we do in machine design, we design anything that has to do with a whole machine. As an example, a car. A car can be seen as like a big machine, has tires, has springs, has fasteners, uh, has uh, has plate elements, has bar elements, beam elements, has all kinds of different type of scenarios. We analyze that statically, dynamically, and maybe even vibration type that's cyclically. So when we think about machine design, and the second part is first is machine, and the second part is design. So when you think about design, what should come to your head is, well, I am not only doing analysis, right? So it's so much of a tendency. Let me just take a simple equation and let's put some numbers in it, and we get some answer out of it. But that's not what we are talking about. We are talking about the moment in which you take something, you do the analysis, you disseminate your work, and you see if that actually is making sense. Many times it takes many iterations to get the results right. In this course, we're going to focus mainly on the structural aspect of it. But the broader picture is that we design something, you're going to have a thermal group, you're going to have an aerodynamic group. Um, yes, the car also is designed for aerodynamic. In case you did not know that, you will have a controls group, you will have a thermal group, loads group, and you got many different groups that actually you have a group that's actually taking care of the budget, the layout. So you got many groups that take into the picture. We are just a small part of that. And so when something comes to us, is basically think about you have an input to us, we do something, and the output is going to somewhere else, somebody else. And that somebody else is going to make sure they go through the chain of command and maybe come back to us again, and that process is a repetitive process. That's why it's a design. Design is iterative in its nature. I like what Albert Einstein said once. He said that knowledge is finite. Uh, the knowledge is finite, but imagination is infinite. And the reason what he really meant by that is you got some knowledge and that's completely finite. But when you start using imagination, that's when the biggest design comes in place. If you think about many of the movies that used to watch yesterday, it wasn't that long ago that we the movies like Star Trek back in the 70s, they just dream about having the phone right here. And nowadays we got Bluetooth and actually um, has evolved in earbuds. And many, as we move on and move on, we thought people would carry their uh, iPads or notepads with them, and nowadays it's in existence. You have that. So I think everything that you dream of, or in imagination, then technology is created to make it happen. Okay, so um, it was a long time ago that we saw cars moving by themselves without any help. And nowadays we see that's basically probably in front of our eyes is coming to reality. So when we talk about machine design, uh, so when we talk about machine design, we are talking about many aspects when we are designing something in structures. So let me tell you a couple of things that we have to keep in mind. Let me switch this to my notepad. So So the first thing I want you to think, when you design something, the very, very first thing you need to know are the external loads. So I need to know my external loads. And that's basically input that you have there. And from the external loads, then we can find the internal loads. And this diagram is very, very important and useful for when you're doing your analysis because actually it follows a systematic approach. Okay, and if you have internal loads, you could probably predict what your external loads were. You can go either way. And this is thanks to Newton's second law. Okay, and then if you have the internal loads, then we can also have stresses. From the internal loads, we find the stresses. And obviously, you can go one way and you can go the other. And this is static equivalence. Okay, through static, we can go one way and we can do the other. And then, if we have our stresses, we can also find our strains in the problem. And we can also go both ways. And this is what we call the material law. Um, material law or the constitutive relationship. Constitutive relationship. And from the strains, then you are able to find your, and obviously you can go both ways, you can find your displacements. So this diagram that you see here, what you're going to see is these are differential equations, by the way. These are nothing else than differential equations. When you see this diagram, basically tells you how everything is connected. It's connected from external loads to finding displacement systematic approach. Now, many times we can relate external loads to displacement methods, and or we can from internal loads we can also find what the displacement methods are. These methods are basically energy methods or energy approaches, and these approaches also involve, let's say, finite element methods. So here you may find like FEA models and semi-analytical models. Some semi-analytical models. So I think this diagram here summarizes what's the scope of this entire class. So you're going to design something. Typically, when you're designing, what you need to know what your stresses are. So this is what you need because your stresses, typically we use stress-based design. So from stresses, we want to see if this is safe. So stresses are important because they tell us if a structure will be safe or not. Now, you cannot have stresses if you don't know the internal loads, and you don't know your internal loads if you don't know your external loads. Okay? So let's go one step back now, and I want you to think about a simple structure. So let's suppose I have a structure. Let's say you got a beam and the beam has some loads on it. Okay, maybe have loads, point loads, moments, and let's suppose the beam is fixed here, just as an example. So when I analyze this beam, the big question would be where do I do my analysis? Which part of all this I do my analysis? Because if you do the analysis at every single point here, every single point throughout your domain is called this, is your domain, in this case for a beam, then it would take you forever to do all your analysis. And how do I know? So the big question is, where do I do my analysis? That's the big question. And because I want to simplify my life. And if there was a way to find where the critical location is, and I did the analysis on the critical location, then we can basically say, if I do everything there, I'm sure the rest of my structure will be safe. Okay, so where do I do my analysis? Actually, takes you to the next uh, point, that basically your analysis is done at the critical location. Okay, so how do I find my critical location? First of all, you will basically do your shear moment diagrams. We will review that in the next class. You do your shear, your moment. You may have torque. You may have your axial load. And from this diagram, uh, basically in this particular problem, probably your diagram looks something like this. Um, I am, well, I'm not sure how it looks like, but just for the sake of the argument, we draw the diagram and maybe it looks something like this. I don't know, maybe it looks something like this, whatever. I'm just making this up. So, and then you have this other thing that looks something like this, and maybe you have a zero torque, maybe you have an axial load that's constant. And basically the goal of this problem is find where the critical location is. It's the location where typically your moment is maximum and your torque is maximum. Okay, these are the critical locations. So once we find a critical location, we're going to go this in detail later. Okay, but right now, just giving you the idea of what we are trying to do. Once we have find the critical location, let's say this is my critical location in X. So I will identify my critical X. From my critical X, now I need to go to my cross section. Let's suppose this was my cross section, right? So I found my location in X. Now I need to know what would be my location in XY. I need to find the point. Is it here? Is it there? Is it there? There? In the middle? Where in this location is that critical location? That particular location is what we're going to call, let's suppose I had a critical location, just as an example. Okay, this is my critical point. Okay, so at the critical point, that's where all your analysis is done. So everything we do in this class, in everything that we do, we are always designing. We are designing at the critical point. Okay? It's important that you understand that. We don't design over a cross section. We don't design over a cross section. We don't design over the entire beam. We just find the critical location in the cross section, find a point, and that's my point of my analysis. That's what we will be doing. So let's go back to our screen. So that's what we are trying to design here. So as you saw here, in order to do this, the first thing I need to know what are my internal loads, right? Because my internal loads will help me identify my critical location. So couple of things, a couple of questions that you should ask yourself now. As we come end of this introductory topic, when I'm designing something, let's suppose I am designing this pen, right? Where am I going to design the pen? Well, every structure has a constraint. Constraint is a location of your boundary conditions, we call them. Maybe it's the restraining in your displacement or rotation. maybe there's a support here. And then every structure needs to have an external load. If it doesn't have loads, then it will not have stresses. There's no displacements. There's no analysis to do in the first place. It's just sitting there doing nothing. But if I apply some type of load, right? So structure needs to have some restraint, okay? Needs to have some loads, and then the structure itself will give me some sense in which I need to find out where my critical location is. And once I identify my critical location, the critical location can be anywhere depending on the load system and the boundary conditions, then I'm going to do a rest of my analysis. Okay, so that would be the topic of your next class. So today this particular topic kept it short. This is just the introductory. What is machine design and what is that we are trying to do? We are in a summary. I'm asking you answer. I would like to ask somebody to answer me. Where are we designing again? Let me hear it. Very good. We are designing at the critical location. What is the critical location? Very good. It is a location, it will be the location in the X direction. Also, it is the point, is the design point is what I'm interested, right? It's the critical location in X and the design point in my cross section. Very good, guys. So, and girls, I will see you in the next topic where we'll discuss and we'll review your shear moment diagrams. Have a nice day.